So you would probably go through a whole slew of pies. You could have like Hershey's or Reese's or French Silk or da 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 da. So pumpkin would be like what? Your eighth?
It wouldn't be food. It don't want that pie.
Hey, M&M's experiment.
Hey, pumpkin pie, get that pie. You can't like bliss pie. Always, I'll take this one first.
Okay, let's bring it together here.
Yeah, I've had two already.
I know it's the last day before spring break, but congratulations on coming to class today. I brought you some M&Ms left over from
Leftover from last year.
no, left over from my MA343 M&M's example. Today we'll finish up ANCOVA.
This one by your foot too.
And if we have time, we'll start logistic regression. But there's a couple of concepts about analysis of covariance that I ran out of time last time before I got to. We showed how to run it in SAS, and we showed how to get the adjusted means, and we talked about what adjusted means are. And now I want to show you mathematically how they work, because to me that gives you the understanding that it's kind of hard to get when you're just looking at the other. So, do you remember what analysis of covariance is? What does that mean?
It's just for continuous variable.
Okay.
So like weight compared to dosage needed or something you can't really put in categories.
Okay, good. So it's ANCOVA with one or more. We only deal with one in this class, but one or more continuous X variable. Right? So you have a grouping variable called a classification variable, like treatment or something like that. But then you can also put in continuous variables called covariance. Right? So these are covariance. This is review from last time. I said all this before. Okay? So in an analysis covariance model, the model itself, there's two ways to display the model, and this is called the cell means method. And it doesn't matter which method you use, so I'm only going to show you this one. But this is the way the book also shows the model for ANCOVA. You get a mean of the ith group, and so.
What is that word? Covariance?
Covariance.
Covariance.
So the mean, mu I, is the population mean of the ith group. So if you got 3 groups of some kind of a drug treatment, you might have placebo, low dose, and high dose. So the mean of the placebo group, the mean of the low dose group, and so on. And then you add to that the covariant part of it, and that has a beta, beta sub 1, and multiplied by xij minus x bar dot plus epsilon ij. Right? So this looks horribly confusing, Greek letters and all that, but if you break it apart, it's not so bad. First of all, the subscripts, ij, what do they represent? What does the subscript I do for us?
Tells you like, well, the group.
Right, that's the group. So Yij, this is, the Yi is the Y variable for a particular subject. So their score, their symptom score or something like that, right? So this is the score for the ith subject, I'm sorry, for the jth subject in the ith group, right? So J is subject within group, and I is group. So I equal 1 dot 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 up to capital I is group, and J equal 1 dot 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 up to n sub I is subject in the ith group. Got it? So then this beta should look kind of familiar. What do we call betas in statistics class? Slopes, right? What'd you say, population? It is a population parameter, and it's the population slope parameter. And it's multiplied by xij. So what is xij?
It's the interaction term. Or, sorry,
It's your variable in
it's the observed.
X variable covariate, right? So that's the covariate of interest. So it might be, remember we did some examples where we had the baseline disease severity as the covariate? So this might be the baseline disease score for the IJ subject. The same subject as Y. This is their value of that X variable. And then subtract X bar with a dot.
grand mean.
The grand mean of the X variable, of the covariate. So ignoring group, what's the overall mean of that X variable? And so I'm measuring, well, how far away from that mean is this person? Right? So if I'm going to adjust their mean or their score, I need to know, well, how far away from the average person are they? If they're way far, I got to move them a long ways. Right? Question?
From now on, when you do the grand mean, can you make the dot like a big dot? Because if I don't have my glasses on, I'd never see that.
Well, if you don't see a subscript on it, it's a grand mean. How about that?
Okay.
Right? Because the book doesn't put a dot at all. It's just
Okay.
X bar. Okay, so now let's see how we use this. To do adjusted means, then, so adjusted means, if they're in group 1, if they're in group 1, then their adjusted mean would be the mean of that group, right? So y bar 1 is the mean of the y variable in group 1 minus beta 1, and I'm going to put a hat on it because we won't know the true value of that parameter, so we're going to have to estimate it from our data, times the distance that that group X mean is from the grand mean. Got it? So then, group 2. What would group 2 be?
Y2 minus.
Yeah.
Okay.
All the same.
Y bar sub 2 minus beta, is it sub 2?
No, still be beta.
No, it's still 1 because there's only one slope parameter, right? Remember our equal slopes assumption? Same slope for all the groups. If we had an interaction term in the model, we could allow for different slopes, and then we'd have a subscript on that beta. But we're not going to fit that model. And then x bar 2 minus x bar dot.
So you don't just put a subscript on it at all, because it's the assumption that they're all the same slope.
Well, if you had another covariate, then it would be beta 2.
Right, but that one, we just leave it alone.
I'd put a little 1 there.
Okay.
Okay? And so on. You do that for however many groups you got. So we got capital I groups. The adjusted mean for each of the groups would be the appropriate subscript for that group. All right? Now, remember the crackers example?
Yeah.
All right, let's go back and look at the crackers example and compute by hand some adjusted means, and then we'll match them to what SAS did. Okay? So, if I go to here, do you remember the scenario for the crackers? We're selling crackers in stores, and we had 3 different types of promotional displays. And now I don't remember what those types were.
One was a big group on the shelf. One was out on
Specialized show.
Specialized.
Okay, I think that was 3, right?
The free samples was 2, or the.
Yeah, they can get free samples. I think that was the second one, and the first one was
Have
Big
special-
display.
just what?
More display.
Yeah, just more shelf space devoted to it, right? So if you want to sell more of this object, then you
Make it bigger.
put a bunch of them out there so that the little kids walk by and they see it. Right? Okay, so we have our analysis of covariance results here. The usual ANCOVA table that you're used to, but now the model has 3 degrees of freedom. I have a treatment factor, or a type of display factor, and how many levels does it have? 3. Is that why there's 3 degrees of freedom for model? No, because that doesn't seem right, does it? Because how many degrees of freedom for type of display? In a one-way ANCOVA,
It's -1.
it's I minus 1. So I is a 3, I would expect a 2 there. But wait, what else did I put in this model?
The covariate.
The covariate, it gets 1 degree of freedom. So the whole model gets 2 degrees of freedom for type, and then 1 for the covariate. And what was the covariate in this case? The name of the variable was last.
The last sales period.
Right.
Comparable sales.
It's how many did they sell during the last period? Because you would think, well, we might want to adjust for that, or control for that. It's another way to say it. So then down in the lower part, you get both type 1, type 3 degree sums of squares. We'll only deal with type 3 in this class, so anything else you can just ignore. Once we get SAS Enterprise Guide back up, you can actually click in check boxes and tell it which types you want. There's a type 2, type 1, 2, 3, and there's even a type 4. In my whole career as a statistician, I've never used type 2 or type 4. So the ones that it gives by default are type 1 and 3. And this is called sequential types. So I put this one in first. Its sums of squares are as if there is no such thing as type. And then type goes in after last goes in. So the bottom row is always the same. This one is added last, right? So this is each of them added after the other one is added. And that's the one we always look at. Right? So you don't have to really remember much about that. Just
What kind was type 3?
variables added last. Okay? And then I added a special option on my model statement to have it give me the parameter estimates. So let me scroll up. And let's look at those parameter estimates. Okay? So here's my model. I got an intercept term. Well, the model that I wrote a minute ago didn't have an intercept term in it. It had mu sub I plus, and then had the covariate part of the model, right? There was no intercept term. This parameterization used an intercept term, which is fine. Since the type 3 has an estimate of 0, then you know, oh, that's my intercept, right? And then these are differences from it. I don't care that you know how to deal with that, right? You'll learn that in MA344, 346, those classes. But the one that I do want here is last. That's my covariate, and its parameter is beta 1, and the estimate of that is 0.89856, if I round to 5 places, right? So, I don't know if I can, nope, I've got to use the mouse to get back to the other window. You guys remembered that number, didn't you? 89856. Okay. So beta 1 hat was, say it again?
0.89856.
Good. 0.89856. Luckily I had it already written in here, so I know you're right. So that is the estimate from the model, right? Then also from the model, let me go back, and I'll show you where I'm getting them, but I haven't written in my paper, so I don't have to have you memorize them. If I scroll down a little bit further, there's our plot with the 3 lines. We looked at that last time, equal slopes. But here are my means, right? So these are my 3 group means. The average number of sales in type 1, type 2, and type 3. Got it? So those means, I'll go back onto the previous page and write them down, and then we'll try to compute the adjusted means ourselves. Boy, well, those were actually the adjusted means I just showed you. The raw means, so what do I mean by raw? If I say the raw means, because I say that a lot, you need to know what I'm talking about. We've got adjusted means and we got raw means.
The means, if you just look at the x variables,
Right.
without adjusting for the code.
At the y variables,
Sorry. Yeah.
right? So raw means are unadjusted means. So means unadjusted. Okay, so here they are. So type 1, 2, and 3, we got 38.2, 36.0, and 27.2. Then the grand mean for y is 33.8. So if I average all of the store's sales and don't worry about the 1, 2, 3 treatment group, then it would be 33.8 cases of crackers sold. I didn't leave room in here, but I'm going to stick in the top of that a y, and then over here an x. So x is our covariant. So the mean number of cases sold in the last period for stores that got type 1 promotion. So that's 23.2, 26.4, and 25.4. Right? Now right away, without doing any analysis, do you notice anything about these numbers?
They don't seem to make a lot of sense.
The covariate is what they sold the last period. Then they did an advertising campaign, and what?
They all increased.
They all increased, right? This one went from 23 cases a month or a week or whatever the time unit was, up to 38. That's a big increase. This one went from 26 to 36. This one went from 25 to 27. Right? So the one that had the lowest sales the first or the last period actually ended up with the highest sales. So it looks to me like there is an important effect due to type. Right? Type seems to matter. Because if all we used was X to predict what the sales would be, then we'd get a different ordering. Now let's compute the means. So the book uses, actually it's not our book, it's that supplement, but they put an asterisk on it for adjusted. So I'll just put a little arrow there. The asterisk is for adjusted. Now, what was the formula for the adjusted mean of the group 1?
It's y bar 1 minus beta hat 1 times the quantity x bar 1 minus the grand mean.
Okay? Oh, I forgot to write the grand mean under here. If you averaged all of the stores together and ignored what group they were in, that's 25.0. Alright, so let's compute it. For group 1, the adjusted mean should be its y mean, the raw y mean, 38.2 minus beta, which is 89856 times 23.2 minus 25. Everybody following me? So do that on your calculator. I hear Emily clicking away over there.
I get 47.72.
47? Not what I got.
I got 39.82.
That's what I got. 39 point, I'll go 4 decimal places, 174, which would be 82 if you round to 2 places. Clean that up a little bit. Okay? So now you do, let's just do, well, I'll tell you what, this half of the room, do the adjusted mean for Y for group 2, and this half of the room do it for group 3, rather than take the time to all do all of them. So you guys do the second one, you guys do the third one. Ready? You're there already?
Yes.
Okay.
26.8406.
Okay.
I think.
34.74. Right? Is anybody disagreeing with any of those? That's actually what I got. I'm going to go ahead and add 2 more decimal places on that one, just so they're all at 4. And it was 34.7420. Okay? So now look at the adjusted means compared to the raw means. I'll circle them. Compare those 3 numbers to these 3 numbers. What happened in the first group?
Increased.
It increased. Why would it have increased? Why do they get the benefit? Group 1 gets to go even higher
Because they sold so little the last period.
because they sold so few the last period. You'd expect them to sell fewer in the next period. Right? They are below the grand mean for X. So if they're below the grand mean for X, this term is negative,
Which makes that positive.
which makes it a positive term. So they get added in. Now this group, both of the other 2 groups, but especially group 2, is above the mean. They're 26.4, so this thing will be positive. So you're going to subtract off some. You're kind of penalizing them for, well, you sold a lot last time, so I'm not going to give you the benefit of just the fact that you sell more overall as a store. In order to compare whether the type of advertising made a difference, you need to adjust back out the fact that they just always sell a lot of crackers.
So when you do, like we're just doing 1, but if you wanted another one, like if you went back another period, is there a way to do that to adjust for the previous 2 periods, or would you
Sure.
just
Yeah,
average
sure.
those 2 and then?
You could do it any way you wanted. You could add a second covariate into the model, but now you've got an issue because that X1 and the new X2 are going to be highly correlated, right? So people might say, well, I'm going to use an average of those 2, put that in as my covariate. That'd be a reasonable thing to do. Other things you could do, but okay. Now let's go back to SAS and look at SAS's LS means. And what do we say LS means?
Least squares.
The least squares means, and it's that,
The central or the grand mean.
well, least squares means is a technical way of saying adjusted means. So LS means are adjusted means. they've used the least squares regression estimate for beta 1 as part of how they compute those means. So if you look at these numbers, 39.8174, 34.7420, and 26.8406, those are exactly what we had. Wow, that's cool, isn't it? Yeah. All right, now, what's this little table?
That's the correlation there.
It's not correlation, but read the title. These things are so cryptic sometimes it takes a little interpretation, so you have to kind of learn how to read this stuff. But it says least squares means for effect type T for HO. T for HO, what the heck? H naught is the null hypothesis, and T is the
T critical value, or the test statistic.
test statistic. So that's the T test statistic. So this is the test statistic for the null hypothesis, LS mean I equal LS mean J. And then here in this little corner it has I/J. So that's telling me that I goes this way, J goes this way. Right? So it's saying they're equal. So the null hypothesis is they're equal. Here's the T value test statistic, and then a slash PR greater than absolute value T. So what it's saying is in each cell there's two numbers. The top one is the T test statistic, the bottom one is the P value. So type 1 is significantly different than type 2. Right? The 4.129 is just a T test statistic. It's not, they sold that many more crackers. Right? But we could get that number easy enough. Then 1 versus 3 is even more significant. It's got a test statistic of 10.76. Remember, a test statistic is number of standard errors away from the null. So you have 10 standard errors, almost 11 standard errors. That's huge. And then this one is type promotion type 2 compared to promotion type 3. And again, highly significant, 6.6 for a test statistic. So they are all different from each other. And that reminds me to talk about the SAS output that you're going to get, or you already got. And some of you came to me asking me, what the heck am I reading here? But I want to turn on this and then go back.
Change to the mouse.
God, there's just too many things to remember. There, now I should be able to write on it.
Yeah, change to the marker.
Thank you. Now I forgot what I was talking about.
SAS output.
Oh, the Bonferroni correction. These have not been corrected for multiple comparisons. Right? I just said, give me the LS means. But I could put an option by saying /BON for Bonferroni, and it would adjust these p-values. But if I wanted to adjust them, what would I need to do?
Divide them by 3.
I need to divide alpha by 3 and compare these against that. Or, equivalently, I can multiply these by 3 and then just compare it against 0.05. So the biggest one of the 3 is 0.0017. If I multiply that by 3, what do you get? I don't know, but it's probably like 0.004 something.
0.0051.
51? Okay, 4. 17 times 3 is 51. Okay, so 0.0051, that's still well below 0.05. So even if I adjust, right, but for the BMD data, the bone marrow density data that you had in the last homework problem, right? It printed the means, and I don't remember what the values were, so we'll just say X bar 1, X bar 2, and actually these should be Y's, but group means. And then it had like an A, and then a B, B, B. Everybody ever seen that? the way you interpret that is it's trying to use letters to draw lines. So SAS is saying, draw a line right there, and anything that's covered by the same line is not significantly different. And then that line only goes to there. So group 1 is different than group 2, and group 1 is different than group 3. Now let's add a fourth group to this and change things up a little bit. If I had this output, A, and then C, 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 there'd be an A in there too. And it's putting an A in between just to fill in the line. It doesn't mean anything, right? So drawing lines like this would go line there, a line there, and a line there. Things that are attached by the same line are not different. Things that are not connected by the same line are different. So 1 is different from what?
2 or 3.
It's different from 3, and it's different than 4. Right? But it's not different than 2.
Yeah.
2 is different from what?
1,
3 and
3.
4, just 4.
I guess
Just
two's,
4.
two's on 2 lines, right?
2 is on 2 lines. 2 is not different than 1. 2 is not different than 3,
But 2 is different.
but it is different from 4.
Okay.
Right? And then 4 is different from 2 and 1. So you have to learn how to read these little things.
Is that like the box plot where they're kind of overlapping?
Kinda, but this is taking into account standard error and basically putting a confidence interval around them and saying, oh, the difference between them is significant or not. You can also ask, I don't think I did here, let's see, mouse. No, I did, good. So I put an option in there to give me the difference between the means. So this has I, J, and then 1, 2. So this is 5.07. Well, look up here at the means. If I take number 1 mean minus number 2 mean, I get 5.07539. Right? And then it puts a confidence interval on that. So what do you notice about that confidence interval?
That
Com-
it contains the mean.
Of course it contains the mean, that's
Yeah.
true, but
That's all I
One
know.
is-
it's always
one
going to
is
be
not
the
included.
mean plus or minus a margin of error.
1 is not included, so they're not the,
It's not 1 that we're worried about.
or,
Remember, this is difference in means. What would the
Oh.
null hypothesis say the difference is?
0.
0.
So 0.
So 0 is not in that interval, therefore it's statistically significant. Yep.
I was going to say it overlaps with the bottom one too. The bottom interval.
Yes.
is 5 and 10.
It does. This confidence interval overlaps with this confidence interval, but since these are differences between means, we can't read into it like we did here. If I put a confidence interval around each of these, then we would definitely look and see, well, this interval overlaps with that one or not. And the fact that all 3 of these were so different from each other, I think all of their confidence intervals would not overlap. That's kind of what these things are, sort of. But none of these confidence intervals contain 0, which is another way of saying all of them are statistically different from each other. Now there is a plot here for LS means. It's really not a real helpful plot, but you do see that, well, type 1 had the highest LS mean. It's just graphically showing those 3 numbers. So, again, it doesn't help you a lot. But I have no idea what that is. Differences for alpha, not significant, significant. I don't know what that is.
these comparisons.
This is new in SAS 9.4. I've never seen this plot before. The previous versions of SAS didn't have any plots given by default. So you only ever saw the ones you asked for. And since I don't know what this plot is, I never asked for it. So I've never seen it before. Okay. I guess that's what I wanted to do. Okay, so that's probably all we need to do with there we go. And I want to get my browser back. That's all we need to really do with analysis of covariance, unless you have any additional questions. Nope? All right. So we will then introduce the next chapter. We won't get very far into this before time is up, but it's called Logistic Regression. Now this topic is taught in a lot more detail in MA346, so this is just a real high-level introduction into what logistic regression is all about. And then our next project we're going to do, we'll look at an article, again from New England Journal of Medicine, that uses logistic regression as their primary analysis and kind of learn how to interpret it. Right? So it's like linear regression, except it's regression with a y variable that is not a continuous numeric variable. Regression where y, that's the dependent variable, is binary. Basically, it's categorical with two levels, right? So, everybody understand what I mean by a binary variable? It only has two values, right? So it might be a variable that indicates response. So I give my treatment, my drug to these groups of patients, and I want to see if which treatment they get can help predict whether they respond or not. So they're what?
Boolean?
It's a Boolean variable. They either respond or they don't. So what we can do is make it a 0, 1 indicator variable. So y is 0 or 1 if a failure, and a 1 if a success. And then you get to define what you mean by failure and success. It might be that a success is dying from this particular cancer. So that's not very successful, but it's whatever you're counting, right? So an ordinary model, yi equal beta 0 plus beta 1 xi plus epsilon I, that's a normal regression model which we learned back in chapter 10, right? With one variable. That won't work. Why won't it work?
Because that suggests a number for y instead of a binary answer.
Right. So if all I have are zeros and ones, remember one of the assumptions was it has to be normally distributed? It isn't going to be normally distributed. Your epsilons are all that really has to be normally distributed, but what is the residuals going to look like? If I predict they're a 1 and they turn out to be a 0, I get a 1. If I predict they're a 1 and they are a 1, it's a 0. And other way around, it's a negative 1. So there's only 3 possible values for the residual. Can't be normally distributed. Right? So it won't work. So what we do instead is we transform yi to a at first I just want to say to a variable that, and I'll put this in quotes, behaves a little better. Right? So where we can get the normal distribution of residuals to look okay. And we do that through the transformation from a 0, 1 variable to the odds of being a 0 or being a 1. Okay, now wait, odds. I've heard that term before. You know what probability is, right? How is odds related to probability?
1 divided by 1 plus probability. No, probability divided by 1 plus probability or something.
Yeah, that's it. So 1 minus probability. Is that
Yeah. Sorry.
So if P equals the probability of success, and I could put a sub I on there if I wanted to say in group I or whatever, but I'm allowing for the X variable in this model to be continuous. It can either be categorical or continuous. So if P is the probability of success, and success means Y is a 1, then the odds of Y equaling a 1 is defined as P over 1 minus P. Right? So if you've ever gone to the racetrack and bet on horses, then they say, well, this horse has 3 to 1 odds. Right? That means the probability of winning is 3 times higher than the probability of losing. So it's the ratio of probabilities of success over probability of failure. That's called odds.
And 100% you're being lied to.
So you can get from odds to probability and back. So if you know the odds for something, then you can convert that to a probability. So if I use O for odds, so let's call this O for odds. That's at the risk of looking like a 0. So solve for O, or solve for P, and it's an easy algebra problem, and what you end up with is that P is equal to odds over 1 plus odds. So if you've been given odds, you can find the probability. If you've been given probability, you can find the odds. Okay? So first we transform Y by talking about the odds of Y instead of Y by itself. So now we've just made the jump from talking about an individual in my study to talking about the probability. So that's group, right? So the error term goes away in the logistic regression model because now I don't have residuals on an individual subject. I can predict the probability for a particular subject, but I can't get an error on that because I don't know, right? So then we take the log, and it's log base E, so natural log of the odds and that is my new dependent variable, my transformed Y. Put a little asterisk by it to say it's the dependent variable, but it's a different one. So the log odds. So we don't typically write log base E, we write
LN.
ln. And I can't write an ln. I have this mental block about ln. I always want to make an H. So it's ln odds. So log odds. And that's called the logit transformation. Logit. And I have no idea where that word comes from because I never remember to go look it up. But it looks to me like, just log it. There you go. That's the logit transformation. And now I can go back to my model, and instead of having Y there, I can put Y star there, but I got to get rid of the error term. Because the error term now doesn't apply, because I'm talking about group averages, probabilities, odds, and not for a single individual. Right? So there's no error term, which is it's strange at first when you're used to regression with residuals and all that. But So this is the log odds of y equal 1 is equal to beta 0 plus beta 1 x I. And I'm going to put a little subscript on that y. The odds that yi, individual I, is a 1. So there's your logistic regression model. So now let's do an example and see how this is done. And we'll start with a simple case of a 2x2 contingency table. So my y variable is 0, 1, success, failure. So there's my 2 columns, but my 2 rows will be the x variable, which is the explanatory variable. And it will also be binary. Right? So that's the simplest case, is when your x is also a binary variable. Right? So this is from an example in our previous textbook that goes into logistic regression. Oh, I'm sorry. This book has logistic regression. So this is an example from our textbook. And this is the odds of binge drinking for males versus females. That seems appropriate for college students. So if I have a 2x2 table, male and female forming the rows, and then binge drink, yes, no. So in this case, a success is binge drinking.
Yeah.
The numbers were 1392 and 3956, 1748. That's not a 4. Jeez. And 6723. And I heard Nate go, geez.
Well, never mind, not anymore.
Yeah. You looked at that number and go, wow, women are just really alcoholics compared to males. But when you total, right, do the marginal totals, you get 5348 males that were in the study and 8471 females. So you had a lot more females in the study, right? Another 50% more. Maybe even a little more. And then the marginal totals of binge drinking, yes or no. For a total in the study of 13,819.
Is that a 579?
That is a 679. Okay, let's compute some conditional probabilities. What's the probability of being a binge drinker if you're male?
It's going to be
So 1392
1392.
over 3140. Divided by 348. If you're male.
If you're male.
If you're
Condition on male means this is your denominator, right? You did the very most common mistake. He went this way. So what probability is that? If I take 1392 over 3140, I got the probability of
Being a male, being a
Being
male.
able to
Good.
binge drink.
being male if you're a binge drinker.
Yeah.
But we want the probability of being a binge drinker if you're a male. So that is 1392 over 5348. So as a decimal, what is that? 0.26028.
Do that.
I did, yeah. Sorry to show off. I did it in my head before I came to class, and I wrote it down on here.
260.
And so this one, without doing the fraction, is 0.20635. So males have a 26% chance of binge drinking. Probably a better way to say that is 26% of males binge drink, 20%, we round to 21% of females. So there is a difference, right? But now let's convert to odds. What's the odds for males?
It's gonna be 0.26028 divided by 1 minus them.
Okay? So the odds for males, I'm going to let's make that a little easier to read. Probability over 1 minus probability. And that equals
0.35187.
35187. Okay? And then, again, without writing out everything for females, get the odds for females. I have 0.26000, which seems unusual, but... Now, one of the things that mathematically you'll learn, or you'll discover, is that when probabilities get really small, these are pretty big for probabilities, but when they get really small, like 0.0 something, then odds and probability are almost identical. But when they're out in the middle, they'll change a fair amount. So the males went from 0.26 probability to 0.35 odds. Females from 0.2 to 0.26. Now, the one thing that we'll do when we get back from spring break, because I'm out of time, is we then form the ratio of the odds. And we get what's called an odds ratio. And we've looked at relative risk, almost the same thing. Relative risk is this many times more likely, but that's a ratio of probabilities. Take the ratio of the odds, you get a similar kind of thing.
So for like the females, it's 0.26. For the odds, is that like just rounding? Is that like the same thing as 1 in 4?
Yeah.
Is that what you'd be saying for that?
Yeah, 1 in 4. You have a 1 in 4 chance. So 1 in every 4 males binge drinks. So the ratio
that's
of
3.
binge drinking to not binge drinking is 0.35.